Hi, I'm Brian Mallow, and I am sitting here with my friend Katie Mack. You may know her as Astro Katie on Twitter, and that's not your handle on Instagram,
It is not my handle on Instagram because somebody else is Astro Katie on Instagram.
No!
I know.
You are Academic Nomad?
Academic Nomad
on Instagram.
Yep.
And if you don't know, Katie Mack is an assistant professor of physics at NC State as of just this past year,
As
a year
of,
ago.
the beginning of 2018.
Yeah.
Yeah.
A little over a year.
Yep.
And you're also a member of...
I'm a member of the Leadership in Public Science cluster. Which,
what is that?
Which is it's an initiative to bring together people who are doing science connected to the public.
Excellent. And that's and you do a lot of outreach. Outreach is definitely a part of it. You do physics, astrophysics, and you bring it to the public. It's no wonder that your Twitter stream is very popular because you write very beautifully and interestingly about astrophysics. So there's a need for that, and it's appreciated, obviously. So we are here because we're going to talk about yesterday's big press release. Although by the time I get this out, I'm going to hopefully get this out tomorrow. So it would be the press release of 2 days ago of this brilliant old news. We've moved on so far from this stunning, although some people have been a little critical, but this very cool image of a black hole.
Yeah.
What is it that we're talking about?
So it's the first ever direct picture of a black hole, direct picture in the sense of actually seeing the aspect of it that makes it a black hole. We've seen black holes all over the universe. We've seen millions of them, but this is different because in this case, we're actually seeing it close enough to be able to say that is definitely a black hole.
Okay.
And that really looks like a black hole.
Now, it's not the first proof of a black hole. No. And so the whole history, maybe we should step back and for some people, just give a little detail about what a black hole is. I think a lot of people know that a black hole, a regular black hole, what we would call a stellar black hole, results from the collapse of a large star at the end of its life.
Yeah.
But it's not how our star is going to end.
Our star is not going to do this, no. So typically to make a black hole, you take a really massive star and you let it burn through all its fuel, all its material, and at some point it gets to the point where it can't burn the last little bit. Basically, it's moving through elements. It's doing fusion, right? So it goes hydrogen to helium, and then it goes higher elements, carbon, nitrogen, oxygen, and so on. When it gets to iron, it doesn't work anymore. That fusion process doesn't make any more energy, and the star collapses on itself. It sort of implodes, and then it creates the supernova, which is just a big explosion of the star. And then the part of it that doesn't get blown out, if it's a big enough, more massive enough star, collapses into a black hole. Yeah. And the idea there is that if you put enough mass into that space, then there's no physical force that can stop it from collapsing under its own gravity. And that becomes a black hole. And a black hole it was first theorized back in the 1780s by this guy, John Mitchell, and then Laplace also talked about these things. The idea that if a star stops producing energy, it collapses. Kind of like if you have a balloon that the air can't push out anymore, it'll collapse, or like a
right, because a star is an active system in equilibrium of the gravity is pulling itself in, but the outward flow of energy, and there's a balance there's a balance. Thankfully it can be balanced for billions of years, or we wouldn't have life on Earth.
Yeah. So that's called hydrostatic equilibrium, if you want to get technical. But
it probably fluctuates a little bit, right?
It does, and depends on the stage of the life of the star. And for our star, we're still balanced pretty well, but as the star gets older and burns through more of its fuel, it's going to change the way the reactions are going. It's going to puff out a little bit. So our star, never going to be a black hole, right? But it will run out of fuel. It'll blow off the outer layers a little bit, and it'll become a white dwarf.
I don't know what the state of astrophysics and astronomy was in the 1700s, but so they didn't have the idea of the not being able to escape it, but they had the idea that, hey, if it runs out of its fuel, it's going to collapse.
Yeah. So there was the process of discovery of what is it that can stop this matter from falling in, right? So with a regular star, the thing that stops the matter from falling in is you have fusion and you have these nuclear processes happening that are producing energy. If at the end of the life of our star, after it sort of puffs up and becomes a red giant, it's going to blow off some outer layers because the fusion's going to get weird, and then at some point the core of the star will be left over, and it'll be held up by basically quantum pressure between electrons. So there's this weird state of matter that you get when you have a really dense, this really dense blob of matter that becomes what's called a white dwarf star.
Okay, so white dwarfs are really dense.
They're really dense.
But atoms are individual atoms. It's that's the extent. It's atoms are pressed up really close against each other.
But
that's it.
Yeah,
the electron shells repel each other.
Well, the electrons,
sort of.
You get sort of electrons mixed in there that are repelling. They're not stable. They're a plasma.
But it's not like the next step before, but a neutron star.
So the next step is a neutron star. So if you have something that's more massive than a white dwarf that runs out of fuel, and you have between, I don't know, up to 3 solar masses, 3 times the mass of the sun.
3 times the mass of our sun.
Yeah, up to around 2 or 3. Then you can have it get even more dense. So then it's the density of the nucleus of the atom.
The repulsion of those electrons isn't strong enough.
Yeah.
It crushes down.
Yeah, and then it's quantum pressure among neutrons.
So then it's pretty much like a solid ball of neutrons, more or less.
Yeah, basically. And it's just the fact that the neutrons don't like to all be in the same place at once that keeps that together. But that's extraordinarily dense.
And a star as big as the sun, which is 1 million Earths, can fit inside the sun.
Yeah, something like that.
If you hollowed it out, but volume-wise, it's about 1 million times bigger than the Earth. Mm-hmm. So we're talking about a star that's a few times bigger than that.
Yeah, but more massive is the main thing. But because
a few times more massive than that. But all of that compressed to a ball that's 20 miles across or something. So that's insane.
So a white dwarf, the mass of the sun would be about the size of the Earth. That's when you got the electrons holding everything up. For neutron stars, it's about the size of a city. And it's just ridiculously dense. But if you have a neutron star, if you have stuff as dense as a neutron star, if you pile more material onto that, then you have too much gravity, and even the neutrons can't hold it all up anymore. And then nothing can stop the collapse.
How many solar masses does a star have to be to?
It's around 3. If it's
around, okay.
Oh no. So the final, So the final object is around 3 solar masses.
After it's blown some of itself off.
But it's something like 8 solar masses is or even larger is the start of the star. When it's still actually burning, and then it collapses.
And really, so when you collapse this idea of a black hole and the event horizon, which I saw some discussion. It's been interesting to see when a story like this goes online and you're on social media and you see a lot of people asking questions, and you get to see people's misunderstandings or not being clear on something. And there was one thing that the event horizon. It's not actually a surface.
No, right.
It's just a certain distance from the center.
Yeah, so let's step back for a second first. So once you have your material all collapsing in, and the idea of that, by the way, comes a little later with a guy called Subramaniam Chandrasekhar. So he's the one who worked out this whole thing about white dwarfs and what they can do, and then he worked out that if you run out of all of those different kinds of pressures, you do collapse completely. And when Einstein heard about this idea, he didn't like it at all. He thought this was a bad idea. So all these people attributing black hole ideas to Einstein, that's not how it went.
Some of the ideas flowed out of relativity.
Well,
but he didn't believe that an actual black hole was a. Why not?
Just because he had some arguments about it would do weird things. It would make things move the speed of light in some kind of weird way, and he just didn't like that idea. So
he wasn't right about everything.
Yeah,
not to knock him.
No, he was right about a lot of things, but
not everything.
But not this one. Yeah, and so Chandrasekhar worked out that this stuff would come to a point. Carl Schwarzschild went and took Einstein's equations and solved them to show that you do get a black hole if and that has these weird properties. And then eventually, they managed to convince Einstein that this is not a terrible idea.
Yeah.
But anyway, so this kind of defining thing about a black hole is that there's a distance from the center of it. Like so everything collapses completely, right? And that becomes what we call a singularity, where you just like everything's collapsing to basically a single point. There's a distance from that singularity based on the mass, the amount of mass you put into it, where if you get closer than that distance, there's nothing that can stop you from going in. So in a sense, the sort of strength of gravity around you has to do with the compactness and the mass of the thing that you're near, right? But so a black hole, you get this basically infinite gravity at the center because it's compacted to a point, right? And so
what does that even mean?
I mean,
I hate
yeah,
it's like, so what happens, so like,
yeah.
What is it crushed out of existence? How can it be?
Basically,
how can a star be crushed down to a point? Is that really what happens?
The problem is you run out of other options because what's going to stop it? Nothing. No force known to physics can stop that from happening.
But where does all the material go?
I mean, so one of Einstein's big ideas was that gravity is just a manifestation of the curvature of space. So you've probably seen these demonstrations where you have like a
rubber
sheet, and then you put a bowling ball in the center. It makes this dip, and then you can take a tennis ball and roll it around and it orbits. That's a visualization of Einstein's idea of gravity, that a massive thing bends the space around it, and then other things moving by respond to that bending of space, and so they follow curved paths. And light does that too. Light will follow the shape of space.
Yeah.
So a black hole is like if you take that bowling ball and you pull it down and down and down and down and just keep on pulling it down, and the curvature just gets infinite, right? So it just goes right.
Yeah.
And then there's nothing you can do to orbit that anymore. At some point you get close enough, you can't orbit, you will fall in. And that's how black holes are. So there's this event horizon where like the speed you would need to go to escape would be faster than the speed of light.
And nothing can do that.
And nothing can do
so
that.
So nothing can escape.
Nothing can escape. And so even light, if it gets that close, will have to go into the center.
But the event horizon is not a surface or anything. It's just a distance from the center, and you could pass it without even knowing.
Yeah, you wouldn't necessarily notice when you go through, depending on how quickly you're going and all that. So it's not a surface. There have been a bunch of arguments about weird things that might happen on the event horizon with
or what it might look like once you get inside.
It gets complicated because there have been arguments about like if there's something strange that happens on the event horizon or not, but depending on whether you believe relativity or quantum mechanics more, and that gets real complicated. We'll keep away from that.
So let's move to.
Yeah.
Because this is a certain kind of black hole.
Yes.
That's a few times, just a few multiple solar masses, something a little bit bigger. But the news story yesterday is about a very different kind of black hole.
Yeah.
It's the kind of black hole that we believe is at the center of pretty much all galaxies, as we've seen them everywhere.
Galaxy,
And they are not 5 or 10 times bigger than the sun or more massive than the sun.
Right.
This one is
6.5 billion times as massive as the sun.
So as massive as the sun is, it's 6 billion times more massive.
Yeah.
It's incomprehensible.
Yeah, I mean, our own galaxy has a black hole at the center of it that's 4 million times as massive as the sun.
4 million, that's more believable. That's more reasonable, 4 million solar masses. So how do we know there's a black hole at the center of our galaxy?
So for our galaxy, we have a lot of really good evidence. Some of the most compelling evidence is the fact that if we zoom in, if we take very careful observations of the center of the galaxy, we see a cluster of stars. And those stars are all orbiting something really, really massive and really, really small.
Yeah, and we know this because we have observed them over a period of like 20 years or something, right?
And you can see animations of these stars, and they'll go boom, like they're really whipping around, and you can measure by how close they get to whatever it is they're orbiting, how small it has to be, and you can measure by the timing and of the orbits, like how massive it has to be, and it's an extremely massive thing that's very, very small. And the only way you can have something really massive and really small is for it to be a black hole.
As far as we know.
Yeah.
Yeah.
And so we've seen that one. Like we've seen the evidence for that one by seeing this. We've also seen evidence for supermassive black holes in the centers of basically every large galaxy we've looked for one, we've seen evidence for supermassive black holes, either through something like orbits of stars, or a lot of times what happens is you have a disk of material falling into the black hole, so it makes like a whirlpool.
Yeah.
Now you have to remember.
And this is for stellar size. So these are called as well, but both could have accretion disks, right?
Yeah.
Like so, because in fact, I forgot. I want to step back to
Cygnus
how we
X1.
know. Yeah, like our first observation. So like black holes were a theory. And we started finding multiple kinds of evidence for it. So these observations of the stars orbiting the center of our galaxy, that's relatively new information. But a couple decades ago, we started seeing some candidates for black holes.
Yeah.
And it's on the idea of like, because people are always like, well, how can you see a black hole?
Right. Well,
and there's a way.
Yeah, and it's because they have disks around them. So you can imagine a black hole as a spherical object that sucks in all the light. So you're never going to see that. But because it's got such strong gravity, it also pulls in the things around it. And if you have something that's pulling stuff in, and that stuff is like gas or dust or pieces of stars or whatever, that's always going to form a disk because of the way that just the way that gravity and like angular momentum work. So you get disks around all sorts of things in astronomy. I mean, even the rings of Saturn are an example of stuff flattened out by the tidal force of the gravity of the object. Right?
I mean, a solar system is like that.
A similar thing. Yeah. So if you have a whole lot of material falling into a black hole, as it's going around, it'll make this disk, and it's like a whirlpool of stuff. And as it's falling in, it's crashing into other parts.
Friction.
There's friction, and it heats up really, really hot. And because the pull of gravity is so strong, it heats up really, really, really hot, and it makes like X-rays
with very high energy, very bright X-rays.
Yeah, and so if you
crucially, this is light. It's not coming from within the event horizon.
Right.
It's the reason we can see it. It's stuff happening just outside it.
Yeah. So it's this disk that's surrounding the black hole, and it's really bright. And so we've seen these sources for decades where there's like a really, really bright, very like point-like object. We can't see, like it's so small from our perspective that all we can see is that it's really bright. And it looks like a single pixel, right?
Yeah.
And so when those are happening in the centers of other galaxies, those are known as quasars, and quasar just comes from quasi-stellar object. That's how it was first.
Before we knew that they were black holes, we were seeing these incredibly bright objects.
Yeah, and they looked like stars in the sense that when you look at a star, it looks like a point and it's bright, and so these things were, but they clearly weren't stars because they had weird sort of absorption lines, stuff like that. Like they looked different, except that they were just a bright point. And so that's how we see black holes in general. We see them as extremely bright sources of light from the distant universe.
And so do I have this right, like historically, that Cygnus X1 was this binary star system that was it was the first candidate that people were like, they were somewhat still theoretical, but Cygnus X1 was such a powerful candidate for this is probably, because there was a star you could see orbiting another one that you couldn't really see.
So Cygnus X1 was just an extremely bright X-ray source. That's why it's X1, right? So it's this extremely bright X-ray source, and they could measure the mass of it by like the
it wasn't a
binary.
Was it a?
I think it was a binary.
Yeah. So like, and it was so some stuff was coming from the other star, but there was this like bright X-ray source.
Yeah, so a lot of the black holes we see are they're so-called X-ray binaries where they're eating the star next to them.
Yeah.
Basically, they're in a binary system with another star, and they're just pulling the atmosphere off the other star and eating
Don't judge.
it. Yeah, just in the accretion disk, and so they light up really bright as X-ray sources. And we actually see sometimes neutron stars do that too. But most of the black holes, like all the black holes in the nearby universe, we see because they're doing that. But then we see black holes in the centers of distant galaxies all over the place, and those are just really, really bright sources very, very far away. So the thing is that for none of these black holes have we ever been able to resolve the region around it to see the disk other than as a bright point of light.
So this is the key. This is what makes this new photo. What's hard to understand and to appreciate. What makes this special is that. Could you elaborate on that? So previously. Because stars are so far away, and as big as they are, they're small for at that distance.
Yeah.
So even when we had like a candidate like Cygnus X1, we couldn't
a black hole,
see very much.
Yeah. So the problem is that, I mean, we've known we've had other evidence that black holes existed, right? But the thing about seeing something like an X-ray binary source or whatever is the only thing you see from the black hole is the brightness of the stuff falling into it, and that just looks like a point. And so in theory, maybe that could be like a solid object that stuff is falling onto. You know, maybe it has a lot of gravity, but you know, it's some kind of weird star in the center. So you wouldn't necessarily, like, you don't.
It doesn't, like, to scientifically, you gotta say that's not conclusive.
Yeah,
because you could possibly be something else that we don't know.
Maybe, right? But like, just because we've never seen it, and we have all these ideas about like, oh, you know, a black hole has this event horizon where even light can't escape, but we'd never seen that happening until now. Now we have seen light not being able to escape the event horizon.
So what is different? So it's incredible because Cygnus X1 is in our galaxy, and our galaxy is about 100,000 light years across. So it's less than that distance. Whereas this, what?
But it's real little.
But it's real little.
Yeah.
But we're talking about a separate galaxy that's 55 million light years away. 55 million light years away. It's an incredible distance, but it's also huge.
Yeah. So the black hole in the center of M87, the galaxy that we were looking at, is like I said, 6.5 billion
solar masses.
And that means that the size of the black hole as measured by the event horizon is bigger than the solar system.
Right.
Okay, so it's a large thing that's still a really hard measurement to make because you're looking really far away, and you know, it's still like you have to have much higher resolution than anything the Hubble Space Telescope can do. And the only way to do that, is to get that kind of resolution, is to use basically every radio telescope on Earth that looks at microwave or millimeter wavelengths, and point them all at this same source, and then somehow synchronize the signals. Because then when you have two telescope dishes that are separated, it's kind of like having one telescope dish that's that big. So you lose something about like the sharpness of the image, or the sort of the sensitivity of the image, but you get the resolution. So the bigger resolution just depends on how far apart.
Size matters with telescopes. And I guess who's the woman who's largely responsible for this data crunch? Lori. I don't know. At MIT, the one who is getting a lot of credit for this image.
There's a postdoc at Harvard who was part of the image processing team. Her name's Katie Bauman.
Katie. And she's not an astrophysicist. She's more of a
computer scientist.
But I heard her say it, that she phrased that in a really interesting way, that we would need to make the observation to try to visualize this supermassive black hole in M87. You would need a lens or a telescope the size of the Earth, and of course that's impossible.
Right.
But in a way, it is possible.
Right. Exactly. So the resolution you can get just depends on the linear size of the telescope.
So they used different radio telescopes, right? In various points on the Earth, and they used them as the Earth turned. So they could make observations from different. Places along there.
It's called Very Long Baseline Interferometry.
Okay.
And
Very Long Baseline. It's
VBLI.
Okay.
And this is something that you can do if you really, really got to have that high resolution. It's a hard thing to do because you're working with interference between the radio waves, which is a complicated thing, but basically you have to have the timing extraordinarily precise in order to be able to match up the images from all of these things. You have to know exactly how far apart they are, exactly what time you're doing the observation, add them up in the right way so that you get, the right kind of combining of the signals. Signal processing wise, it's really, really difficult, really, really complicated. So it's a really,
this requires a round, not flat Earth that rotates. Just one more piece of evidence for a thing we should not even be talking about, especially the contrast. 2 2,000-year-old science versus yesterday's science. Anyway.
Yeah. Anyway.
So it was very complex imaging, and it required all this. It required astrophysicists, theoreticians, practitioners, and it also required computer scientists.
Because you had to somehow put together all these signals, make them work together in the right kind of way, process the data. There were several algorithms that were used, written by different people, that were kind of compared to each other so that they could check everything. They wanted to really make sure they weren't accidentally putting in their expectation of what the image would see.
Right. So by using different teams using different methods, and the methods gave the same answer.
Yeah, that's the idea. And then they had people doing simulations of what this image should look like, and then comparing the simulations to the data to learn something.
They did pretty well, didn't they?
Yeah, they did amazingly well. So the simulations, it's astonishing.
The black hole that was in the movie Interstellar, for which the Nobel Prize winning astrophysicist Kip Thorne helped as a consultant, was a very similar sort of simulation, right? It's pretty remarkably
pretty much the
accurate.
same kind of simulation,
That's what we thought it should look like.
Right. So the weird thing about what's happening when you look at a black hole that has an accretion disk is that, let's say that you were looking at it edge on, so the black hole is here, the disk is here, then it wouldn't look like there's a line here and then there's something, like a line and then something dark. What it would look like is that you have the line there from the disk, but then you also have the light from behind the black hole being bent around, so it kind of bends up the disk on either side, and that's what
this part gets really hard to visualize and like to think in 3 dimensions. Because it's. Because you can draw, but it's a sphere.
Yeah, so the sphere is bending the light around itself, and so it creates. So it shows you the back of the accretion disk on top and on bottom of
so let's say facing towards the camera. Like, so you have this disk, and there's some light back here that it should shoot out that way. Some light that should shoot out in all these, but space is so bent.
It gets bent
that some of it's curved over there, and some of it's curved right back towards us.
Yeah, exactly. So some light goes that way, and some light goes that way if you're looking edge on. But then crucially, so crucially, there's a dark part right there. So if you're looking from that direction, you'll have like an arc here, and an arc here, and then a dark bit there.
Why is there a dark bit?
So the reason for that is that you're looking at the part where the black hole, if the light tried to go that way, the black hole would just eat it.
Right. So it either eats it or it bends it in.
Yeah, so it can deflect. So it can deflect some light, but if it doesn't deflect it enough, it just eats the light. And then that part's dark.
So some gets bent just enough to be here, and some under. But and some would get bent too much and go in, and there's this area, so that blackness, what we're seeing, they're calling it a shadow.
That's a shadow, that's the black hole.
But it's not technically a shadow like what we think of as a shadow.
No, what it is, because there is stuff behind the black hole. There's not light being, like cast against something that's blocking the light. It's not blocking the light, it's eating the light, it's swallowing the light. And so in these cases where you're looking edge on, you see this blackness because that's where any light that could have been coming from that region, it was too close to the black hole, it went right in. So that's what the interstellar black hole looks like. The one that we just saw is tilted more like this. So we're looking at it more like face on, like there's the disk and then there's the black hole in the middle. And in that case, you see the shadow as like sort of a circle, or a slightly squished circle. So you see the disk as this sort of ring. And that's just the disk really close to the black hole, about to fall in, like heating up. And then you don't see the part where the light was shining toward the black hole, or even shining in another direction, but got too close and it fell right in. And so the darkness you see in the middle of that image is light that the black hole removed from the universe.
Removed from the universe. So what does happen? Matter and energy, the whole thing about conservation of energy, that things aren't created or destroyed. What happens to the stuff that goes? And isn't this a big question, that Stephen Hawking and others argued about?
So there is a question of does that information go away somehow? But what happens to the light is it just contributes to the mass of the black hole. Or if you want to think about it, it contributes to the curvature of space that is what the black hole is. The black hole is basically at this point just pure space curvature. I mean, think again about that illustration of like you have a rubber sheet and you just pull it down and down and down. At some point, it doesn't matter that there was a bowling ball there anymore. The point is that it's just curvature of space, and that's an analogy because that's a sort of two-dimensional sheet being pulled down in a third dimension. We're talking about space just contracting itself. But yeah, so if you get too close, then the light gets pulled in. So this ring, the striking thing about this ring is that if there were like a star at the center, some kind of object at the center that was pulling this accretion disk in and creating this X-ray light, then it would be bright in the middle. The only thing that can make it dark in the middle is if something is pulling the light away from our view and hiding it behind this event horizon.
So that's why, even though we've had multiple types of evidence for black holes.
Yeah.
So first of all, the theory has stood up for a long time, and then we've seen things like Cygnus X1 and X-ray sources. We've seen these things, these stars, and those stars orbiting are the black hole in our galaxy. Some of them are accelerated to like a third the speed of light or something.
I don't remember the numbers.
It's
but they're real
great.
fast,
Like, so imagine a star, about the size of the sun, being like, what force can propel it to a fraction of the speed of light?
We've even seen stars ripped apart by black holes.
Crazy.
We've seen like shocks or like bursts of X-rays.
So even though we've had all those evidences, scientists like to maintain a certain amount of skepticism that is like, all right, we're pretty sure this means black holes are real, black holes are real, but this one is even more solid.
This is just another really extremely good piece of evidence. I mean, I would say that the point at which it became silly to even think about any possibility that black holes didn't exist was when LIGO detected the black hole gravitational waves. So LIGO instrument, laser interferometry gravitational wave observatory, they're measuring ripples in space. So they're measuring gravitational waves, and they saw two black holes orbiting each other, colliding with each other, becoming a new black hole, radiating 3 solar masses worth of energy out in gravitational waves, and then kind of wobbling until it became like a stable black hole. That matched the theory so perfectly, like nothing else could have explained.
And this was a prediction of Einstein's.
That was
this is something he did believe in.
Yeah, I mean the numerical models he couldn't have done, but gravitational waves he did believe in. Although he didn't believe that they could be detectable, at least for a long time.
Well, because
it's a really hard experiment.
It's absurd. Like I still haven't wrapped my mind around this at all. This is a couple of years old now, and it's why Kip Thorne won a Nobel Prize because he worked on this as well.
Yeah.
And that in order to be barely detectable by the highest technology today, the only gravitational waves they could detect required giant black holes colliding. So anything.
These ones were like 30 times the mass of the sun.
But still, so it took those kind of masses. So everything, we're generating gravitational waves.
This is gravitational waves.
And the Earth is and the sun is, but in order to be detectable by our today's state of the art, it took two giant masses colliding to create ripple. So, and gravitational waves are ripples in space-time.
They're ripples in space-time.
Is space-time a thing? Like, a lot of people, I know I could keep you here all night if we, it's
so space-time is, it's basically...
It's not just empty space.
It's basically a grid system, but it's one that responds to what you're doing inside it. So it's, the way you move through time is affected by the way you're moving through space. And space-time can sort of change its shape, responding to the masses and so on. So it's... it's sort of, it has has characteristics of being a kind of malleable stuff, even though it's not like an object, but it is malleable in a way that it responds to what's happening in it. Anyway, so we knew about black holes for a long time. We've had all these pieces of evidence. The LIGO detections were really, really solid evidence, but this one to me is kind of special. I mean. Yeah, it's another piece of evidence for black holes. We're learning stuff about like the mass of this black hole. We're learning about the properties of the accretion and all of that. But to me, there's something really amazing about just seeing it, because everybody talks about black holes as like, they're so massive that even light cannot escape. But now we're seeing that happen. We're seeing light that's happening near the black hole, and it cannot escape. It's being pulled in and hidden from us forever by the event horizon. So we're seeing the darkness where there's an object from which light cannot escape.
Yeah, like previously we saw this high frequency X-ray radiation coming off the accretion disk around a black hole, but we couldn't resolve anything better than that. We're just seeing that light from just outside a black hole.
Yeah.
And so suddenly we're seeing it's just that much more intimate a connection to the black hole, right?
And that darkness is just, it's just such a cool idea that there is something in the universe that will take light and hide it from us forever. Like, it just removes it from the observable universe and it's gone. I mean, I think that's amazing. And just to see that and to know, because you know that, the theory all works out, and this is, you can write down the equations, like you can get it from a physics point of view.
Yeah.
But there is something really different about seeing it, about being like, oh yeah, that actually happens, That's actually a real thing that happens in the universe. Light is devoured by these objects.
Yeah. So scientists, especially in physics and astrophysics, have been really, really excited by this.
Yeah.
I think in a way that it's hard for people that aren't astrophysicists to appreciate.
Right. Yeah.
Part of it probably comes from, there's a thing to be appreciated when your theory makes predictions and then your observations show that it's like, wow, it's exactly what we predicted.
Right. And I was saying before about these simulations, they made simulations of what it would look like if there's an accretion disk around a black hole at different angles, and they took one of their simulations for the angle that they expect, they blur it out a little bit to make it look like what the telescope should see. You compare that to the image of what the telescope actually saw, and you can't tell them apart.
Yeah.
It's astonishing how well the observation matches the theory, and the theory is just based on Einstein's equations.
I like what you said about, like, the way you're the only one I've heard say this about, like, it's like this, it's the light disappearing into black holes, and it actually, so it made me think. We can talk about, because you're currently writing a book.
I am.
And it's about the ways the universe might end.
Yes.
And surely one of them is probably the way. You probably have a favorite or what's the name of the book?
The book is called The End of Everything.
The End of Everything.
It'll be out next year.
And it literally everything. You do mean everything.
Absolutely everything.
And it'll be out when?
Next year.
Next year.
Probably it'll be published officially in June or July. It'll be available for pre-order sometime early in 2020.
Excellent. And you're still writing it, right?
I'm still writing it.
So what I was thinking, it made me think of Olber's paradox, this idea, which I never understood what the answer to it is, but there's this idea that if you look out into the night sky, in an infinite universe, every possible point should eventually lead to a star.
Right.
So why isn't the entire night sky bright?
Right.
Is there an answer?
There is, yeah.
What is the answer to that?
So the answer is that the universe is not infinitely old, and so we don't know if it's infinitely big, but we do know it's not infinitely old. And so if you look far enough away, you look so far back in time that there wasn't a galaxy there yet.
Okay, so that's interesting.
Yeah.
What your new comment about this image made me think is that, but I mean, it's counteracted by that if you look out in any direction, that eventually in an infinite universe, you should hit a black hole, so that all light could eventually disappear into black holes.
Well, if you wait long enough, if you leave a galaxy alone long enough, then all the stuff in the galaxy will start to kind of degrade its orbits and end up in the black hole.
Yeah.
Eventually, like the universe, eventually everything will kind of collapse into black holes because, let's say you have a really stable orbit of two objects. At some point, they're going to hit enough pieces of dust that the orbits will decay a little bit.
Yeah.
And if you wait extraordinarily long, they can fall into the center and become a black hole. But then the black holes themselves will evaporate through Hawking radiation, which is a whole other thing.
Right.
And those will shrink and decay, and then, then they'll
I have a question. I have a question. So
Okay.
here's something we didn't really address that's crucial. We discussed how what we call a stellar-sized black hole occurs
Right.
from the death of a large star.
Yeah.
But how does a supermassive black hole, like, so what do we know? If I'm not mistaken, we don't really know the answer to this.
That's
that
right.
how do galaxies form? How do they happen to have, and your specialty, you're writing a book on the end of the year, but your specialty is dark matter.
Yeah.
And so that's crucial to galaxy formation as far as we know as well. So how do galaxies form? How do they come to have, it's not just it doesn't seem like a star died
No.
and then accumulated more and more, and to the extent that it became
It's
6
a
billion
hard-
solar masses
yeah,
at the middle of each galaxy.
It's a hard problem because, so we know a couple of things. We know that black holes and galaxies, their growth is somehow connected. So if we look at the masses of galaxies compared to the masses of their black holes, certain properties of the galaxy correspond to the mass of the black hole. So there are these connections, there are these relationships that suggest that as the black hole is growing, the galaxy is growing too. And we also know that black holes in galaxies, some of them form very early in the universe. I mean, we see black holes of like 1 billion times the mass of the sun within the first billion years of the universe, and it's hard to get that much matter into that small space that quickly, because in the very early universe like that, like you haven't had much time, and it's not easy to throw things into a black hole. Like like let's say you have a black hole that's just like a star. A star collapses, make a black hole, a few solar masses. Pulling matter in takes a while because the matter
People
has to
have a
come in
misconception
and fall in and,
that they're like vacuum cleaners
Yeah,
and that,
no.
that something is a black hole and it sucks up, but it's no different from any body.
yeah. So if
Unless you get really close to it.
Right, exactly. If our star turned into a black hole, if the sun turned into a black hole, aside from the fact that there would be no more light coming from it, we wouldn't really notice. We would keep orbiting.
Yeah, gravitationally it would be the same. It would have the same mass.
Yeah, just in a smaller
And at
space.
this distance, it would be the same.
Yeah.
If you got
real
a certain
close,
closeness to it,
then you would
it
fall
would
in.
be different.
Right. But yeah, so if you have a star that becomes a black hole, unless there's a lot of matter nearby, it's not going to fall in. It's not going to make the star. It's not going to make that black hole grow.
So how does it grow that big?
So you have to. So we don't know how they get this big that early. Some of it's accretion. Some of it is just gas. When galaxies collide, that can help grow the black hole because the collision between the galaxies throws a lot of mass, and like a lot of gas and stars and stuff into chaos, and some of that can be eaten by the black holes. And sometimes black holes merging with each other, as LIGO saw, that brings up the mass. But
how does that give one at the center of each galaxy? It's very mysterious.
It's a difficult problem. I mean, so it's some combination of accreting gas and dust and stars and planets or whatever, and also merging of smaller black holes into the big ones, or merging of the black holes in centers of two galaxies would merge when those two galaxies merge. So there are several different ways that it happens, but making it happen quickly enough and tying it so closely to how the galaxy is growing, this is an area that's we're still trying to figure that out.
Yeah. Well, so just wrapping up with, once again, you are Astro Katie on Twitter and Academic Nomad on Instagram.
Yep.
Anywhere else that we could find you?
I have a Facebook page. I don't update it very much, but it's facebook.com/AstroKatie.
Okay.
And I'm my website is astrokatie.com.
Okay. But just on a very personal level, what was yesterday like for you? Yesterday, the press, like a lot of people, you were ready and tuned in to the press conference.
Oh yeah.
And so just tell me what it was like for an astrophysicist who's really interested in this area. What was yesterday like for you?
I didn't really know what to expect. I didn't expect a really, really sharp image, obviously, but I didn't think it would be quite as impressive as it was. I didn't think it would be as detailed as it was when it came out. And so when the image was shown, I was surprised. I was surprised by how clearly you could see the ring and the dark part in the center of the shadow. I didn't think it would be quite that clear. I thought you would have to kind of squint and guess. So that was kind of amazing. And then from there, it was just trying to figure out, like, okay, how massive is this thing? How far away is it? Like, what are we really seeing? And then, really digging into, okay, what's really happening with the light rays here? How can I picture this? Because I wanted to explain it to people, like, because it's exciting to me, And so, and when I see something exciting happen, I want to share it with other people. So I read a whole bunch of papers about like how the photon orbits happen around black holes, and the fact that the shadow is not the size of the event horizon, it's a little bigger because of the way that there's a distance out to which a photon can orbit in a circle around a black hole and a distance to which it can't, and so like all these kinds of things. And so it was a lot of just kind of like trying to read as much as I could and figure out like what's the really exciting thing, what are we learning from this, what do we know now that we didn't know before?
Yeah.
Just to try to get on top of it, because it was a really exciting thing. And so I actually spent most of the day yesterday on a train. Because I had been...
You were coming home, yeah.
I was coming home. I'd been in D.C. And so I was sitting on this Amtrak, just reading papers and looking at Twitter and trying to like...
A train like in Einstein's thought
like that.
thought experiments that put him on the trail to relativity.
Yeah, and then I was sort of hiding in the train's vestibule talking to the BBC, I mean...
Really?
Yeah.
You did some interviews?
Yeah.
So like a lot of times, like something like this, it's what it means to a scientist is one thing. So, well, what do you want non-scientists to take away from this?
I guess I think that like it's just kind of an amazing achievement to see this thing, but I think what we can take away from this is how we can use this huge collaboration. It's like 200 people, 8 different telescopes, working together
around the world, different countries.
Around this world, like 20 countries I think were involved.
Wow.
Putting it together so precisely, like it's a big effort. It's taken decades to get all this together, to really be able to do this.
Science thrives on international cooperation.
It does, yeah. So there's that, and then there's just the fact that this is a really cool thing that exists out in nature that is, a fantastical object, so far from our experience. And I really like to try to get across just the wonder of this is an extremely bizarre object. But it's not just a thought experiment. It's not just like, oh, wouldn't it be neat if this happened? This is real, and we can see it, and it's in the universe. And like we can watch this happen. We can watch light not being able to escape from the black hole. Like that is a really amazing thing to me.
Yeah. Well, thanks for talking to me about it. I feel like I understand some of it a little better.
Good.
Astro Katie, Katie Mack, Dr. Katie Mack.
Sure.
And I'm Brian Mallow, not a doctor, and I'm at Science Comedian everywhere, so thanks for watching. Feel free to share this, and good night.
Bye. All right.
Cool. I don't know how long we went.